Okay, in this video we're going to look at two more two-dimensional simplex algorithm problems, and we're also going to address what happens when we have a 0 in a ratio test in the second example. Okay, so we will get to that. Okay, so wanted to go through simplex questions a little bit more quickly than what I have done in the previous videos. So here we've got our linear program. Here I've solved it graphically, okay, and done my vertex testing, chosen my vertex, and then got my solution. Okay, so this is a solution that we're going to be aiming to get to with simplex algorithm. And what I'm going to do is I'm going to keep referring to this graph as we go through this this algorithm. Okay, so new page. We've got our objective function. We've got 4 constraints, and then we've also got this extra bit of request for the question, which is to say to pivot on an element from the x column first. Okay, so sometimes a question can say that, and we'll have a look at why when we get there. Okay, so for now we're going to draw up the initial tableau. So the objective equation becomes 1 minus 2x minus 3y, nothing else is nothing. And then we have this constraint, which is 1x, 1y, plus a slack is 52. The next one is 2x plus a y, plus another slack is 100. Then we have an x and a 4y, plus a third slack is another 100. And then finally we have 3x, 28y, and a fourth slack, and that's 588. Okay, so there's my initial tableau. I do have a whole video on setting up the initial tableau, so please do check that out if you weren't sure where any of that came from. Okay, so now we are going to conduct a ratio test because we are told to pivot on the x column first. Now, if we weren't told this, we would be pivoting on the y column first because that's got the most negative entry in it. And if we go to the graph, then ultimately we need to get to the point C, which is here. Now, if we move in the y direction first, we're going to go to A, then B, then C. Whereas if we move in the x direction first, we're just going to go to E, then D, then C. Either way, it's 3 iterations away from the answer. So we will be doing 3 iterations of simplex, but going via E makes the maths a little bit easier in the tables. Now, you want to know that at the beginning of simplex, and sometimes a question can ask you to do that. So just bear in mind that it can shift your initial pivot column. Okay, so we're going to conduct a ratio test. So Greek letter rho. The ratio test is the right-hand side divided by the entry. So that is 52 divided by 1, which is 52. 100 divided by 2 is 50. 100 divided by 1 is 100. And 588 divided by 3, that's 196. Okay, so of the ratio test, we are going to choose the smallest of those. So let's just remind ourselves what these ratio test values do. With simplex, we start at the origin. We have chosen to move in the x direction, so we're going to move this way. And we can either move 50, which will take us to here, or we can move 52, which will take us to here, or we can move 100, which will take us to here, or we can move 196, which will take us to the intersect of this line with the x-axis. It'll be over here somewhere. So we want to choose the smallest of those because we don't want to shoot out of the feasible region. So we stop at E, which is why we choose this value as our answer from the ratio test. So pivot column, pivot row, that's our pivot. And now we're going to pivot about that point. So let's pivot. All right, so I'm going to put in the row operations on the left-hand side. So this is the pivot row here, the third row down. So what I'm going to do is I'm going to take that row and I'm just going to divide it by 2. So row 3, which is the row 3 from the previous table, divided by 2, that's going to equal the pivot row. So when I use PI for the rest of these 4 lines, I am referring to this row. Okay. So I'm just going to take this row divided by 2, so I get 0, 1, a half, 0, a half, 0, 0, 50. Okay. Now I want to add and subtract multiples of this row to the other 4 rows such that everything in this column is a 0. So I'm going to make that a 0, a 0, a 0, and a 0. Okay. Now, nice and quick, anything that was a pivot before, except for S2, because that's on the pivot row, so S1, S3, S4, and P, they're going to remain the 1s and 0s that they are, because I'm going to be adding multiples of 0 to those rows. So I'll go and get 1, 0, 0, 0 there. S1 is 0, 1, 0, 0. S3, 0, 0, 0, 1, 0. And then S4 is 0, 0, 0, 1. Okay, nice and quick to get those ones in. So then it's just the 12 elements left to fill out. Okay, so I want to make this a 0. So I'm going to do row 1, which is the row 1 from the previous table. And I'm going to add 3 times the pivot row to get rid of that 3. Okay, so minus 3 plus 3 times the pivot row is a half. Oh, no, I'm not, because that's my chosen pivot. It's row 1 plus 2 times the pivot row. Sorry, I'm getting rid of this. Sorry, habit of choosing the most negative. Sorry, minus 2 plus 2 times 1 is 0. So that'll make that. So I need to do minus 3 plus 2 times a half. That's going to leave a minus 2. 0 plus 2 times a half. That's a 1. And then 0 plus 2 times 50 is 100. Okay. Now this row here, this one's got a 1 there, so I need to subtract the pivot row. So it's going to be row 2, so it's row 2 from the previous table, subtract PI, which is defined as this row here. So I'm going to do 1 subtract a half is a half. 0 subtract a half is minus a half. And then 52 subtract 50 is 2. And then this row, again, there's a 1 there, so I just need to do row 4, subtract the pivot row. So it's 4 minus a half is 7 halves. Then I've got 0 minus a half is minus a half. And then I've got 100 minus 50 is 50. And then finally, I've got this bottom row here. I've got a 3 there, so I need to do row 5, subtract 3 times the pivot to get rid of that 3. So 28 minus 3 times half, that's 56 halves. So I'm subtracting 3 of those, so that's going to be 53 halves. Just leave it as fractions, but because it's a half, you could put a 0.5, I guess. Although that's not what I've got on my table. Maybe that's just rounded. Yeah, okay, let's stick with that. 1 minus a half is, 0 minus a half is minus a half. Oh no, I'm doing 3 of that, so 3 halves. And then I've got 588 minus 3 times 50, so it's 150. So that's going to be 438. Okay, so there's my second tableau. Okay, now that I've got my second tableau, I decide, am I at the optimal vertex? And the answer is no, because I have a negative entry in my objective array. So I'm going to repeat the algorithm, choosing this column now as my pivot column, because that's the only negative conductor ratio test. So 2 divided by a half is 4. 50 divided by a half is 100. 50 divided by 7 halves, that comes out, do that on the calculator. 50 divided by 3.5, there you go, 14.3. And then 438 divided by 26.5 is 16.5. Okay, so the smallest of those is the number 4. So going back to my graph again, let's just have a look at exactly what's going on there. I'm choosing the y value to increase. So from here, if I'm going to increase the y value, it means I'm going to be going up. So I'm going to be going along this boundary here. I can go up to y is 4, which would be the point D. Or I can go up, well, the next y value I could have gone up by is 14.3. So that would be the intersect there. Then 16.5, so that would be moving up to there. Or I could increase by 100, and that would be going from E all the way up to that intersect there. So I've increased y by 100. Just like before, I don't want to shoot out of the feasible region, so I have to choose the smallest positive value from the ratio test. So that is the number 4. So that's why I'm choosing this one. So this is now going to take me from the point E to the point D. Okay, so that's my pivot, and we've already done an iteration, so I've already done that one, okay, for us, so we can see kind of where we're going with it. Okay, it does make me doubt whether that should be a 53 or a 52.5 though. My crib sheet here I printed off from Excel, so it's rounded. Okay, I probably should just check that. So I'm going to times that by 2, and then to get rid of that I need to do 53 times it. Yes, no, it is a 53, that's fine. Okay, right, now that I'm here, I am at the point D on my graph. Now the point D was when X is 48 and Y is 4, gives me a p-value of 108, and we can see when we read off the table, X is 48, Y is 4, and P is 108. Okay. It also gives me the values of these slack variables, which is how much slack I've got with the bottom 2 constraints from the problem. Okay, so S3 is 36 and S4 is 332. Okay, but we have a negative value in our objective row, which means we can still make improvements. So we're going to choose that as our pivot column, and then we're going to conduct a ratio test. So 4 divided by -1 is -4, 48 divided by 1 is 48, 36 divided by 3 is 12, and 332 divided by 25, 332 divided by 25 is 13.28. Okay, now at this point, we go back to our definition back in a couple of videos ago. For the ratio test, we choose the smallest non-negative. So that is this. We reject the 4. We don't want to do that. We choose the smallest non-negative, so I'm going to choose this one. Now I'm moving in an S2 direction, so this is a little bit unclear as to exactly what that means. But let's just look at the graph. I'm at the point D, and S2 was the slack variable of one of the constraints, which means I'm going to be looking to increase that, that value. So because I'm going to be moving from D to C, I'm moving off this boundary. So what moving in S2 does means I'm going to be moving on this boundary. That's the only other boundary I'm on. So I'm going to be moving in this direction, okay, because that's moving me away from this boundary. Now I can either move -4 in that direction, which is actually going to push me this way. So increasing S2 by -4 is going to bring me out of the feasible region. It's going to hit me at this point here, which is no good, which is why we don't choose a negative value. We only ever choose positive values from the ratio test. Okay. Now moving 12, which is the smallest value from the ratio test, is going to put me from D to C. If I chose to move 13.28, that would move me from D to this intersect here, which is outside the feasible region. So again, no good. And the final one was moving 48. So if I increased S2 by 48, that would push me all the way out to here. And again, that's no good. That's 52 on the y-axis outside of the feasible region. So we choose the smallest positive value, and that would take us to the point C. Okay, so that's why we've chosen to do that. All right. Okay, now from there, we have this is our pivot, and then the we can conduct our iteration of Simplex. So I'm just going to do this nice and quick. So what was a pivot before is now still a pivot. So 1, 0, 0, 0, 0, that's always going to be the case for the objective variable. 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, and this one here is going to remain as 0, 0, 0, 0, 1. This column here is going to be what this column was. Okay, it's the whole idea of pivoting about S2, this one here. So this one will move to here, and then all of these will be zeros. So they'll disappear. So we're left with these numbers to fill out. I'm going to divide this row by 3, so that our pivot is the number 1. So that's going to be minus 7/3. That's going to be positive 1/3, and that's going to be 12. Okay, so there's the bulk of the setup done. And now it's the trickier bit. We need to subtract multiples of this row to make sure that all of these are the number 0. So top row, add the pivot row will give us a 0 value here, and that's going to give us 5/3, 1/3, and 120. Again, we've got a -1 there, so if I do row 2 plus the pivot, that'll get rid of that -1 to make it a 0. So I need to do 2 minus 7/3, which is minus 1/3. 0 plus 1/3 is 1/3. And then 4 plus 12 is 16. And then this one we're going to subtract now because we want to make that a 0. So it's this row subtract the pivot. So -1 minus 7/3 is 4/3. That minus that is 1/3, that was a 0. And then we've got 48 minus 12 is 36. And then finally, I need to do 25 times the pivot. So row 5 subtract 25 times the pivot row. That's going to give me 16/3 there, minus 25/3 there, and the number 32 there. Okay, feel free to check that. If I made a mistake there, then just drop a message in the comments. Okay, so we are now at our objective, our optimal vertex because there are no negatives in the objective row. So we can read off our values. P, top row, P is 120. This occurs when X is 36. X is 36 and Y is 16. Okay, so that's the solution to the linear program. And then we've also got some slack values. So S2 is 12, which means we are not on the second constraint, and S4 is 32, which means we are not on the fourth constraint. But S1 and S3, they're both 0, which means we are lying on the first and third constraint. So that is the intersect C. That is the intersect of the first and third constraint, those two. Okay. And we can see that indeed X is 36, Y is 16, and P was 120, which is exactly the values we got here. Okay, so that's the first example. That's out of the way. Second one. Okay, again, two-dimensional case. We're going to do some 3D cases in the next video. Okay, so maximise x plus 2y, so these constraints. We're looking at graphing these. There we go, so there's our graph of the feasible region, and we've selected the point B. So that comes out, P is 40, and that occurs when x is 16 and y is 12. Okay, so that's solving it graphically, and we're going to be doing that using Simplex as well. So let's have a look at how this one plays out with the Simplex algorithm. Okay. So again, we're going to set up our initial tableau. To do that, the top objective row becomes the top row of our table. So we're going to have a P minus an X minus 2Y. No slacks is nothing to start with. Y is less than or equal to X. So what I'm going to do, so I'm just going to do Y minus X is less than or equal to 0. Okay, so that I can replace that with a slack. So Y minus X plus a slack variable is equal to 0. Okay. And I'd have to do y minus x. I can't do x minus y is greater than or equal to 0 because although the origin satisfies it, that wouldn't be a slack variable. That would be what's called a surplus variable, and we'll look at that in more detail when we do two-stage simplex a bit later on. Okay, so this is what the this constraint will become. So we're going to do minus x plus a y plus a slack is nothing to start with. This one is just 1y and a slack is less than 12. And then this one, we've got 3x plus a y plus a slack is less than 60. Okay, so there's our initial tableau for this problem. Now we're going to select pivot column. So it's the most negative value in the pivot row, in the objective row. We're not told anything else, so that is what we go with. Conduct a ratio test. That's 0 divided by 1, which is 0, 12 divided by 1, which is 12, and then 60 divided by 1, which is 60. Now, up until now, I've said sometimes we choose a 0 and sometimes we don't. This is one of those situations where we do choose the 0. Now, the reason for this is because the entrant in the pivot column is positive. Okay, that is what that is when we choose the number 0, when the entrant in the pivot column is positive. If the entrant in the pivot column was negative, we would not choose that 0. You could look at this as being a positive 0. So 0 divided by a positive number, it's a positive 0. That's another way to consider it. Or if this was a negative number, we could just rule it out of the ratio test altogether. You just ignore it. Okay, you can only pivot on something that is a positive number. Okay. All right, everything else just proceeds as usual. So we are going to, well, that's already a 1, so don't change anything there. So that's going to be 0, minus 1, 1, 1, 0, 0, 0. Now we're going to add and subtract multiples of this row to the other 3 rows to make this column zeros everywhere else. That means that S2 will remain as that, and S3 will remain as that, and the P is always that. So let's just leave those 9 values to fill out. Okay, so we're going to add 2 multiples of this row to this top row to make that a 0. So that's going to be a minus 3. That's going to be the number 2. That's going to be the number 0. Then we've got, I think I should have circled that, sorry. Then we're going to do this row, subtract that. So 0 subtract minus 1 is positive 1. 0 subtract 1 is negative 1. And 12 subtract 0 is 12. And then we're also going to do the same thing here. So 1 subtract 1 is 0. 3 subtract minus 1 is 4. 0 subtract 1 is minus 1. And 1 subtract 0 is 1. Done that. 60 divided minus 0 is still 60. Okay, so there's our second tableau. That's the table after 1 iteration of Simplex. And let's just have a look at where we are graphically. So X and S1, those are the 2 columns full of junk. So we're going to set that, the non-basic variables, we're going to set those to both be the number 0. Okay, that's our choice. That leaves us with the other 4 to be locked in, which tells us that P is 0, Y is 0, S2 is 12, and S3 is 60. Now, what's curious about this is X is 0, because that's basic, non-basic, and Y is 0, because the right-hand side is 0, which means we are still at the origin. We have moved from 0, 0 to 0, 0. And it's not a mistake. We have moved in the simplex, which is a multi-dimensional shape. We just haven't appeared to move on the XY plane. A way to illustrate this, which I like to tell my students, is imagine a cube. Okay, you've got a cube. Obviously, it's got a number of vertices. Now we could move from this front corner of the cube back to this corner of the cube. Now, if I draw it like that, then that's fine. You can see that movement because you've gone back into itself. But if I rotate the cube such that you can only see the front face, then doing that movement, going back to the back side of the cube, you're moving from here and it looks like you haven't moved. But you have, you've just moved in a different dimension, you've moved down. That's exactly what has gone on here, just with this multi-dimensional simplex that we are dealing with. Okay, bearing in mind we've got 6 variables, so we are in 6-dimensional space. So you can't visualize that, which is the problem with simplex. So although we doesn't appear to have moved on the XY plane, we have moved in the simplex. Okay, so although we're at x equals 0, y equals 0, we have moved in the simplex. This can occur when multiple constraints intersect. So here, we've got the constraint y equals 0 and x equals 0, and the constraint y equals x. So 3 constraints are meeting at this point, which means there are 3 pairs of constraints meeting all along that same point, which they are separate points in the simplex. They're 3 different points, but from our point of view, it just looks like 1 point. Okay, so that's when this kind of thing occurs. I wanted to tidy that up and clarify that a little bit. Okay, so now we just repeat simplex again. So we're going to choose this one here as our pivot column, because that is the only one that contains a negative value in the objective row. Conduct a ratio test. 0 divided by minus 1 is 0. 12 divided by 1 is 12. And 60 divided by 4 is 15. Okay, so we have a choice. We can either move 0 in the x direction, 12 in the x direction, or 15 in the x direction. And out of those, we're going to this time reject the 0 and choose this one. And the reason we are going to reject this 0 is because this is a negative 0, if you like. And the reason for that is because the entrant is negative in the pivot column. So we're doing 0 divided by minus 1, so therefore that is negative 0. Or, another way to look at it, that's a negative value, so you never choose it as a pivot. Okay, that's when we reject the 0, when you have a negative value in the pivot column. So we're going to choose the smallest positive value now, it's just a 12, so therefore this is going to be our pivot. Okay, all right, now let's carry out the iteration. That's already a 1, so I don't need to do anything there. So it's going to be 0, 1, 0, minus 1, 1, 0, 12. And then we need to get rid of everything else in that column. So that's going to be a 0, a 0, a 0, a 0, a 1, a 0. This one's going to remain as 0, 0, 0, 1. And this is going to remain as 1, 0, 0. So we've just got those 9 values now to fill out. Okay, so I'm going to make everything in this column a 0. So this row 1 plus 3 times the pivot. So minus positive 2 plus 3 times minus 1 is minus 1. 0 plus 3 times 1 is 3. And 0 plus 3 times 12 is 36. This one here is a minus 1 in my row 2 there. So to get rid of that, I'm going to do this row plus the pivot. So 1 plus minus 1 is 0. 0 plus 1 is 1, and 0 plus 12 is 12. And then finally this one down here, I need to do 4 times the pivot and subtract it. So minus 1 minus 4 times minus 1 is positive 3. 0 minus 4 times 1 is minus 4. And then 60 minus 48 is 12. Okay, so we are now here. Okay, so notice now we're moving in the x direction. We have increased our y value as well. And that's because although we're increasing x, we're not moving along this constraint. We're actually moving along this constraint. So this is still increasing x, it just increases y as well. And that's because we moved for our initial move. So we're not at the actual origin. We moved in that simplex dimension first. So that gives us this table here. We're still not the optimal vertex because there's a negative 1 there. But we are at the point x is 12, y is 12, p is 36. And that occurs at the point A. So x is 12, y is 12, p is 36. So we have moved to here. Okay, and we know b is optimal because we've done it graphically. So let's just carry out that last and final iteration. We're going to choose that one as our pivot column because that's the only negative value in the objective row. Conduct a ratio test. 12 divided by 0 is infinite. 12 divided by minus 1 is minus 12. And 12 divided by 3 is 4. So we choose the smallest positive. Okay, there's no zeros to worry about. So that's clearly this one. And so therefore this is going to be our next pivot. Divide that by 3. Add that to this row and this row to get rid of those minus 1s. And we end up with this tableau here. This is our final tableau. And we can read off our values. P is 40. X is 16. Y is 12, and S1 is 4. Our non-basic variables are S2 and S3, which is 0. Okay, so that's the solution to our linear program by the simplex method, and we can see that is true because it's a two-dimensional case that we've done graphically. All right. I know this is a long video, but I really hope that's helped you with executing simplex. And in an examination, you're usually only asked to do 1 or 2 iterations of Simplex. You wouldn't be asked to do all 4 tableaus like in this one, or like I had in question 1. All right. My next video, we're going to look at a 3D case and a 4D case, so we can't look at them graphically, but this whole build-up that I've been doing is so that we can do it without a graphical method. All right. Thanks very much for watching, and comment if you have any questions.